In this lesson, what we're doing is we're just demonstrating the difference between an average rate of change and an instantaneous rate of change. So before we get started, remember an average rate of change is just the slope of a secant line, and we represent that as f of b minus f of a over b minus a. So given a function on a closed interval from a to b, we can find the slope of those two or the slope that connects those two endpoints, and that's f of b minus f of a over b minus a, or rise over run. Instantaneous rate of change is very similar, except we're finding the slope of a line that's tangent to the function. So this is where the idea of derivative comes in. So our slope is equal to f prime of a specific x value c, and we represent that as the limit as delta x goes to 0 for f of c plus delta x minus f of c divided by delta x. Let's look at an example just to demonstrate this. So given the function f of x equals 2x squared minus 1, we want to find the average rate of change over the closed interval 0 to 2, and we're also going to find the instantaneous rate of change at x equals 1. So over here, we'll find a rock. So remember, average rate of change on my interval from 0 to 2, I just take f of b minus f of a, and I'm going to divide it by b minus a, where in this case a is 0 and b is 2. So I'm going to look at 2 times 2 squared minus 1 minus f of a, which is 2 times 0 squared minus 1, and that's going to be divided by 2 minus 0. So what this gives me is 2 squared is 4, 4 times 2 is 8, 8 minus 1 is 7. Minus 0 squared is 0, 0 times 2 is still 0, minus 1 is negative 1, and that's divided by 2. So I have 7 minus negative 1, which is 8, and 8 divided by 2 is 4. So the average rate of change for my function 2x squared minus 1 on the closed interval 0 to 2 is 4. If I wanted to demonstrate the instantaneous rate of change, or IROC, what I want to do is I want to find the derivative of my function at the value 1, since I'm finding the instantaneous rate of change at x equals 1. So my goal then is to find f prime of 1. What that's equal to is the limit as delta x goes to 0 for the function f of x plus delta x minus f of x divided by delta x. In this case, I'm plugging in my value of 1, so f prime of 1 is equal to the limit as delta x goes to 0 for f of 1 plus delta x minus f of 1 divided by delta x. So I need to find out what f of 1 plus delta x is and what f of 1 is equal to. So f prime of x is equal to the limit as delta x goes to 0. So my function is 2x squared minus 1, and I'm going to plug in 1 plus delta x. So I get 2 times 1 plus delta x, quantity squared, minus 1, minus f of 1 is 2 times 1 squared minus 1, and that's going to be divided by delta x. So f prime of 1 is the limit as delta x goes to 0. I can expand my binomial, so this is 2 times 1 squared, which is 1, plus 2 delta x, so 1 times delta x plus delta x times 1, plus delta x squared, minus 1, and then I'm going to have minus 1 squared is 1, 1 times 2 is 2, and 2 minus 1 is 1. And all of that's divided by delta x. So what I can do is rewrite this f prime of 1 equals the limit as delta x goes to 0. So here I have 2 plus 4 delta x plus 2 delta x squared minus 1 divided by delta x. So now that everything's expanded and distributed, I can begin simplifying. So f prime of 1 is limit as delta x goes to 0. So 2 minus 1 is 0. So on the top, I'm left with 4 delta x plus 2 delta x squared over delta x. I can factor out my delta x from the top, and it's going to cancel with the one on the bottom. So I have limit as delta x goes to 0 for delta x times 4 plus 2 delta x divided by delta x. Delta x's cancel. So f prime of 1 is going to be equal to limit as delta x goes to 0 for 4 plus 2 delta x. And keep in mind, I'm finding the limit as delta x goes to 0, so I'm going to use direct evaluation to plug 0 in for delta x. So f prime of 1 is equal to the limit as delta x goes to 0 for 4 plus 2 delta x. So I plug in 0 for delta x, so this is 4 times plus 2 times 0, which is 4. So my instantaneous rate of change is also 4. And so this just happens to be a coincidence that these two equal the same thing. But the cool thing here is that we can take our function, find the average rate of change, and then also find the instantaneous rate of change at a specific point using this idea of a derivative.